So in this video, we're going to introduce the AMD CDNA assembly. We want to see what the machine sees. So one thing before we start is that the assembly languages for AMD GPUs are very similar. We're just using CDNA as an example here. For GCN 3, GCN 4, GCN 5, CDNA, RDNA, they have very similar assembly structure, although they are not exactly compatible with each other. We want to understand why we want to understand the assembly language. So you can gain a deeper understanding about the GPU architecture, so you know the GPU instructions and how GPUs execute those instructions. Sometimes you debug GPU program and really need to deal with the assembly language. That is what the ROCm debugger supports. And sometimes you want to write code with extreme performance, so you want to write in assembly languages directly so you have the most control on the hardware. The first thing we want to do is to extract the assembly from the heap program. Every heap program that is compiled by heapcc generates something called a fat binary. A fat binary is a combination of the CPU binary and the GPU binary program. In a Linux system, it's an ELF file that is embedded in another ELF file. The outer ELF file is for the CPU binary, and the inner ELF file is for the GPU binary. Let's assume our program is named as main. We want to extract the GPU binary from the CPU binary so that we can analyze the GPU assembly. There are several tools that we can use to extract the binary. For example, we can use this command first. This command will reveal what kernels are there in the binary. So it will dump something like this. This is a URI, a Unified Resource Identifier, that is in this file called main and has a certain offset with a certain size. Those are marked in bytes. So those represents that this kernel is located in this file at this particular position. Now we can use rock obj extract to extract this binary, this GPU binary. So we can use rock obj extract with the file name and the offset and the size. This command will dump the binary. If we want to disassemble it, we can use llvm obj dump with MCPU GFX 908. It really depends on which particular chip you are using. So you have to match the binary with the GPU chip that you are using. With this disassemble command, then you can eventually generate a bin.co, which stands for code object. Note that you cannot use the official LLVM to perform this task. You have to use the LLVM that is provided in the ROCm project. ROCm provides a convenient way that we can simply use rock obj disassemble target ID GFX 908 in the main to dump all the kernels in that main program. So we want to talk about the execution model before we start talking about the language. As we discussed before, the basic element in a kernel is a thread. A group thread can be organized into blocks. A block is typically a 64 to 1024 threads group. But your GPU is not very good at processing these variable size blocks. So GPU uses an intermediate element that is called wavefront. NVIDIA terminology is also called warp. In AMD terminology is called wavefront. So wavefront is 64 threads for GCN and CDNA GPUs, and is 32 threads for RDNA GPUs. Why wavefront concept is important is that for every instruction that is in the assembly language is in the unit of wavefront. For example, we have this instruction VADDU32. So it's add two numbers in the unsigned 32 format. We're basically adding V1 and V2 and store the result into V0. This is one instruction, but it's actually 64 operations. Because this instruction is at wavefront level, the same operation applies to all the threads in this wavefront. And different threads in the wavefront may have different values that is stored in the V1 and the V2 register. As we can represent this V register using the register ID and thread ID, this simple instruction is actually 64 operations that performs an element-wise register adding operation. What are the register and instruction types that is provided by the AMD assembly? there are scalar instructions. So for example, we have this instruction called SADDU32. It's very similar to the previous instruction. The only difference is the prefix. Previously it was V, now it's S. This S represents it's a scalar instruction. So when we use scalar instructions, we have to use scalar registers. That is S1, S2, S0. Those registers are different from V1, V2, V0. So those registers are shared by the threads in a wave front. So for example, thread 1, thread 2, when they are accessing S1, they are accessing the same register that is storing the same value. So these scalar registers can be accessed by both scalar instructions and the vector instructions as we introduced before. There are also some special registers. Those are also considered as scalar registers. For example, we have program counter, execution mask, VCC, SCC, VM count, LG, KM count. We will introduce the purpose of these registers later. So here's an example of a shifted copy program. We can look at the kernel on the top. So it's a shifted copy. The first thing we want to do is to get the global thread ID. So we read the data from the in buffer. We shift every element by 4. Then we store everything into the out buffer. And below is the assembly that matches to this shifted copy program. This program is very simple and the assembly is very short. We're actually removing some instructions at the beginning so that we can talk about the core part easily. Let's just talk instruction by instruction. At the beginning, we have 2 registers. As you can see, the first instruction is a load register. But while we're loading at the beginning, right, we have to have this S4 and 5 pre-initialized that stores some value. Here, S4 and 5 stores the address of the kernel arguments. That is the in pointer and the out pointer. And the in pointer is stored in S0 and 1. The output pointer is stored in S2 and 3. So V2 and 3 are storing the global thread ID. In this instruction, we're shifting left by 2 digits. That is equivalent to multiply by 4. It basically converts the global ID into the offset to the buffers. Next, we see this swait count instruction. In this swait count, we're waiting a particular counter that is LGKM counter. L stands for local, G stands for global, K stands for constant, M is memory. So it's basically one counter that is representing 3 different parts of the memory. Throughout the tutorial, global memory is not that important here. This is not the GPU memory. L, local memory, is for local data share. We will introduce it later. K is for constant memory. It's basically a memory that a scalar instruction is accessing. When we're executing the first line of code as load dword by 4, we're actually incrementing this LGKM count by 1. So even before this data returns, we can perform the shifting left operation, where there's no dependency on S0 and 3. But in the next instruction, after the swait count, we have SADDU32 and where we need to use S0 and S1. Right? So we have to add an explicit synchronization there to wait for the data to return. So when the data returns, the LGKM counter decrement by 1. So this line 3 here is a compiler added synchronization to guarantee that there is no violation in the dependency of the instructions. So next, we see examples of using scalar instructions. The first instruction adds 16 to S0, and the second instruction is an SADDC. It considers carry from the previous instruction. The previous instruction, if it needs to carry data, it will store 1 into the SCC register. Basically, it's adding S0 and 1 by 16. So this is actually performing the GID plus 4 operation. That is the calculating offset for the in pointer. we need to perform some more address calculation, but this time we're moving to vector register because at this point we need to start to have different register values for different threads. The first instruction here is vmove. We're moving the data from S1 to V5. Now we're basically performing the same ADD and ADDC operation, that is adding S0 and V5 to V2 and 3. It's basically calculating the offset for different threads. Now similarly, in the 3 instruction below is actually calculating the output pointer or the output address for each thread. Next, we want to check this store and load operation. We see another example for latency hiding. So on the first line here, we load the data. Similar as the example before, when we execute this global load instruction, we increment the vector memory count by 1. Now whenever the data returns, we decrement the counter by 1. And in the swait count line, we wait until this VM count becomes 0. So here this global load is a vector load instruction. This V0 and 1 stores address, but this address can be different from thread to thread. And the loaded data can be different from thread to thread and is stored in V4. Eventually, when we have the data that is stored in V4, we store the data back to V0 and 1. And finally, all the GPU program in AMD assembly ends with this line as end program. When we execute that line, that means this wavefront is completed and the resources can be freed from the compute unit. Next, let's see another example that is slightly more complex than this one. Let's consider some branching. We want to see how GPU handles branching. And this is a copy kernel. Now it's a copy kernel that only copies the value that is greater than 0. So how can GPU handle this type of branching operation, this value-dependent branching operation? And this is the assembly. As you can see, it's slightly longer than the previous one. We're not showing the whole assembly in this single slide, but that's pretty much the whole assembly here. We want to see this load operation. We don't want to consider those address calculation anymore. We have seen how it is done before. And this load is a larger load. It's d-word by 2. So we're loading 8 bytes at once. Why? It's because the data type is different in this particular example. In previous example, we're dealing with floating point data, that is single precision floating point data. And in this example, we're dealing with double precision floating point data. Then we perform a comparison operation. We compare if 0 is less than V4 and 5. It matches to the condition in the if clause. And here VCC is a 64-bit scalar register, works in a way that each bit represents one thread. So this is a vector comparison operation, and we're comparing the V45 value of each thread with 0. We see this very special instruction called as and save execute B64. What it's actually doing is it moves the execution mask, the previous execution mask, into the S4 and 5 register. We'll talk about execution mask later. Right now, you can just consider it as a scalar register. And we're storing the value of VCC into EXEC vector. So next, we consider this branching instruction. It's a conditional branching instruction as represented by the letter C before the branch letter. And the condition here is EXECZ, which stands for if execution mask equals 0. When the execution mask is 0, or previous comparison result VCC is all 0, that means there's no thread that actually fulfills the condition. If no thread fulfills the condition, we don't really need to execute the instruction below. We can just simply skip the rest of the instruction and come to the end of the program. If that condition holds, we'll jump to this basic block called BB02. And BB02 is basically a compiler added label, so it can help us to jump to that particular location. Here, we see the effect of execution mask. So here, only the thread with a value greater than 0 will have an execution mask bit that is 1. So if the corresponding execution mask has bit 1, these instructions will execute. Otherwise, if the execution mask has a corresponding bit of 0, these lines of code will still execute but will not take effect. So these vector values will not be updated and the store will not happen for those threads. Then finally, we see this line as OR B64 is an operation that recovers the execution mask. In this particular example, we don't have any other instructions, but if we have other instructions, we need to continue to execute. So we need to recover the execution mask that is stored in S4 and 5. So here we want to talk about this predicated execution and how execution mask works. We do something before, or we compare TID when thread ID is smaller than 32. Let's assume there are 64 threads. We do something. Then otherwise, we do something else. Then we do something after it. So all the instructions are for the whole wavefront. If we perform this do this operation, all the threads in the wavefront needs to execute this line. But we don't want some of the threads that doesn't fulfill the condition to take effect, right? So we want to use this execution mask to represent which instruction, which thread will take effect. At the beginning, execution mask starts with 0FFF and OF, that is 64 ones. Be careful, if your block is smaller than 64 size, your execution mask may not start with OF. It will mark those non-existing threads as 0 in execution mask, so that none of the execution of those threads will take effect. Then when we execute this if condition, we still have the execution mask with OF, but we start to have thread divergence. Then this execution mask will be set to 0 for the upper threads and F for the lower threads. Then we perform this operation and only the lower 32 threads will take effect. In the else condition, we flip the bit mask and we perform this do that operation. And finally, after this if statement, we recover the execution mask and mark everything back to OF. So here are some performance implications. It basically takes the same number of cycles for your program. It basically takes the same number of cycles for your compute unit to execute one instruction regardless the state of the execution mask. So if we have a execution mask that is 0, 0, 0, all 0, but there's only one in it, so only one of the thread will take effect. So it will actually have 1 over 64 effective performance. So your effective performance is actually much lower than the theoretical performance that your compute unit can calculate. So thread divergence, for this reason, is something that you want to avoid as much as possible.